Hello and welcome. So, you've probably seen the periodic table, right? It's usually hanging up in a science classroom, looking a little like a super complicated calendar. But it is so much more than that. It's actually one of the most powerful tools we have for understanding, well, everything. So today, let's crack its code.
I mean, what if I told you that there's a hidden logic, a secret code that can literally predict how all the basic stuff of the universe is going to behave? A code that explains why some things are explosive and others just aren't.
Well, that code is the periodic table. It's basically a master list of every single type of fundamental building block in the universe, which we call elements. An element is just a pure substance, think gold, or the oxygen you're breathing, that you just can't break down into anything simpler. And the way the table organizes them, that's the key to everything.
To start cracking this code, we're going to look at the big patterns first. The most obvious clues that the table gives us just by looking at it. Seriously, think of this thing as the universe's ultimate cheat sheet. Okay, so the first big pattern is this major split in personality. See, most of the elements are metals. You know what they're like, usually solid, they're shiny, and they're great at conducting electricity. And then you've got their total opposites, the nonmetals. They can be gases or maybe dull, brittle solids that are really bad at conducting anything. This simple division is like the first layer of the code. Now, the table is a grid, right? The horizontal rows are called periods. But the real magic, the real secret, is in the vertical columns. We call those groups. And you should think of the groups as families, where every single element in that column shares a really similar personality. And some of these families have very distinct characters. And when I say distinct, I mean it. These families have predictable personalities. Some are super social and reactive, while others are complete loners. Let's meet a couple of the most extreme examples, shall we?
First up, let's meet a family way over on the far left side of the table. Their entire personality, their whole reason for being, can pretty much be summed up in just two words.
These are the alkali metals, over in Group 1. They're soft, they're shiny, and they are unbelievably reactive. How reactive? Well, if you were to drop a tiny piece of potassium into water, the reaction is so intense, so vigorous, that it creates flammable hydrogen gas and immediately sets it on fire. Yeah, definitely a family with an explosive personality.
Okay, now, let's take a trip to the complete opposite side of the table. We're going to meet a family whose whole vibe could not be more different.
These are the noble gases, all the way over in Group 18. They are the absolute definition of aloof. They're so stable and so content with themselves that they almost never react with anything. They just float on by, totally unbothered. And their extreme stability, that is a huge clue in our mystery. So, this brings us to the most important question, right? Why? What is it about those alkali metals that makes them so desperate to react while the noble gases just couldn't care less? The answer isn't on the surface of the table anymore. To find it, we have to go deeper. To really crack this code, we need to zoom in. I mean, way in. We've got to look at the structure of a single atom, the tiny little unit that makes up every single element. Okay, so inside every atom, you've got three key players. In the center, in this dense little core called the nucleus, you find positive protons and neutral neutrons. And then you have these tiny negative electrons just zipping around the outside in orbits. The number of protons, by the way, is what makes an element what it is. And just to give you an idea of what an atom's really like, it's almost all empty space. All the heavy stuff, all the mass is packed into that tiny little nucleus. In fact, if you could somehow get rid of all the empty space in all of your atoms, you'd shrink down to be smaller than a penny, but you'd still weigh exactly the same. Wild, right? So the secret to why elements behave so differently isn't in the nucleus. The secret, the answer to our entire mystery, is all about how those electrons are arranged on the outside. It all comes down to the electrons. You see, electrons fill up these orbits, or shells, around the nucleus, and they follow a few really simple rules. The first, innermost shell, it can only hold 2 electrons, max. Once that one's full, the next shell out can hold up to 8, and the third shell can also hold 8. It's kind of like seating guests at a series of tables with a limited number of chairs. Let's see how this actually works. We'll start with hydrogen. It's atomic number 1, so it has 1 proton and 1 electron. That single little electron takes the first available seat in that first innermost shell. Simple enough. Next up, helium, atomic number 2.
It has 2 protons and 2 electrons. So both of its electrons fit perfectly into that first shell. And look at that, the first shell is now completely full. This is a very, very important detail. Remember that.
So, what happens with lithium? Atomic number 3? It's got 3 electrons. The first 2 fill up that first shell, no problem. But now there's no more room. So, that third electron has to go start a whole new shell, all by itself. And hey, notice where lithium is on the table? It's the very first element in the second row, period 2. That's not a coincidence.
Okay, we have all the pieces of the puzzle, we have our element families with their crazy personalities, and we have electrons filling up shells. Now let's put it all together and solve this thing once and for all.
And here it is. This is the solution to the whole mystery. An atom's stability, its happiness if you will, is all about having a full outer shell of electrons. Remember the alkali metals like lithium? They have one lonely electron in that outer shell. They are desperate to get rid of it so they can have a stable, full shell underneath. That's what makes them so violently reactive. But the noble gases, they already have a completely full outer shell. They are perfectly content. They have zero reason to react with anything.
So the whole point is this. The periodic table isn't just a random chart. It is a map of electron structures. An element's group number, its column, tells you exactly how many electrons are in its outer shell. And that number determines its entire personality. The secret code we've been hunting for, it's the number of outer electrons. That's it.
And the table is so powerful, we can actually use it to make predictions. Chemists are always trying to create new, super heavy elements. So here's a thought to leave you with. If they finally created element 119, where do you think it would go on the table? And based on everything you know now, what kind of personality would you expect it to have?